Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And today we will be talking about how you can estimate the building thermal energy demand. Because when you do a geothermal simulation in GHEtool, one of the main tabs you need to fill in is the thermal demand of your building, of your project. So let's dive a little bit deeper into this topic and discuss how you can obtain this data. So within GHEtool, you can enter the thermal demand in two resolutions, let's say. You have either hourly resolution or you have a monthly resolution. And you even have the option to do it on a yearly or a multi-year timescale. Now, what do we mean by that is that typically you enter your hourly load or your monthly load for one particular year, and you assume that for the whole simulation period, this energy profile just repeats itself. This is what we call the traditional yearly timescale. Now, if you have, for example, a project that will be built in multiple phases, for example, apartment buildings on a collective system, you can end up with a situation where your thermal demand changes over time. And then you can enter or you can input the load data, both hourly and monthly, on a multi-year timescale. But this is a topic for a future video. So today we will assume that you calculate or you come up with a load profile for your building and that it repeats over the whole simulation period. Now let's discuss both this hourly and monthly resolution. So if you have an hourly resolution, you can calculate the bore field, the required temperatures and required bore field size in the most accurate way as possible. Now, there is an asterisk behind accurate because it's not by definition the case that if you have data with an hourly resolution, with a high resolution, that it's by definition also more accurate. It's, for example, this hourly data can be obtained with a dynamic simulation by measurement of perhaps similar buildings, but it's always important to take into account occupancy behavior and whether or not your data is representative for the building you're actually trying to simulate. Because if you obtain this data with high accuracy for a building that's more or less your particular building, it can be that your simulation, your geothermal simulation, is not that accurate after all. But given the fact, or assuming that your hourly profile is really representative for your building, your HVAC system and the climate, then we can say that this resolution can give you also the most accurate bore field temperatures. And here below we see again a temperature or a load profile for such an hourly simulation where you have hourly loads for both heating and cooling. Most often, however, we do not have this type of resolution and we work with a monthly resolution, or you enter the values on the yearly level and GHEtool makes it into a monthly resolution. So designing geothermal system with a monthly resolution is ideal for feasibility studies and also, to be honest, for most simple designs where simply this hourly resolution is not available. And what you need is 5 different pieces of information. You need peak powers for both heating and cooling, as well as the energy demand for heating and cooling, and if that's applicable to your project as well, the domestic hot water consumption. So let's go over these different options and see how you can obtain these values. So let's start with the peak power in heating. What is it exactly? So the peak power in heating you need to enter in GHEtool is simply the peak power of your heat pump. If you have a heat pump of 10 kilowatts, then the peak power in heating for your building is 10 kilowatts, because it's limited by the size of the heat pump. Now, how you come up with the size of the heat pump, typically that's determined by building standards in your region. For example, in Belgium, the heat pump is typically sized based on the static heat loss of the building at minus 8 degrees Celsius outside temperature. So we calculate the static heat loss and based on that we size the heat pump. And this heat pump maximum power is then also the maximum power for your peak demand in heating. Now, in case you have a modulating heat pump, you can actually set the peak power of the heating to be a lower value. So imagine you have 7 kilowatts of static heat loss, and you say, well, let's take a heat pump of 8 kilowatts. Yeah, then you should design your geothermal system to work with 8 kilowatts. And because if you install a heat pump of 8 kilowatts, it can demand 8 kilowatts, and your bore field should be designed for that. But of course, if you say, well, the static heat loss is only 7 kilowatts, so in theory, my building will need at maximum this 7 kilowatts, you can set it as a setting in your heat pump, ask your manufacturer, you can set it to be maximum 7 kilowatts, and then you can also design with 7 kilowatts. Or for example, if you have an emission system which only has a certain amount of power it can deliver, you can also set your peak power to that value in order to make sure that you do not oversize your geothermal bore field. In case you do not have the peak power in this really early stage, we have certain rule of thumbs based on watt per square meter. This watt per square meter can be based on, for example, the emission system. If you have floor heating, we know that's between 30 and 50 watts per square meter that it can deliver. For example, you know it by similar buildings. If you install an office building, you can, for example, have a different rule of thumb than for apartments or for schools, let's say. In the article, we have a couple of these rule of thumbs written down, so if you're interested, you can find them there. And the last thing about this peak power is also the simultaneity. Now, we discussed about it already quite extensively in a previous article, which is also linked in the description. But what we said there is that if we have, for example, 100 buildings or apartments connected to the same bore field, that your peak power for your collective bore field is not simply the sum of all your buildings, because they do not occur at the same time. But that was covered last time. Now, for the peak power in cooling, it's more or less the same story, except we can make a distinction here between different regions of the world, let's say. So first of all, you have buildings where the geothermal system is actually designed for cooling. Now, what do I mean by that? It's for the warmer regions where cooling is actually the most important energy consumer in the HVAC system. And then you follow the same reasoning as for peak power in heating. So you typically have a standard by which you can calculate the peak demand for cooling, and you size your emission system and your bore field based on that. But in other countries, cooling, especially passive cooling, is more like a nice to have. So what you do is you size your geothermal system based on the heating demand and the peak heating, and then you have a certain emission system, and then you calculate what can this emission system deliver in terms of cooling, and that value you take as the maximum power for cooling. So you do not design your system for cooling, but you work with what you have. So for example, if you have floor heating and it was designed to work with a heat pump, or it was designed to cope with a certain peak power for heating demand, we know that this floor cooling can also give us around 15 to 25 watts per square meter. So therefore, we know if we have the building size also what the peak power in cooling can be. And again, here for an early stage, we typically have also rule of thumbs for watt per square meter, based, for example, on the emission system, but also there are rule of thumbs for office buildings, schools, etc. So this is for the peak power in cooling. Now, the other side of the story is not the peak power, but it's the energy demand. And there are, again, a couple of ways to calculate this. The first one is using full load hours. So what we do here is we say, well, imagine we have a heat pump of 10 kilowatts, and we say it has 1,000 full load hours. Then we know that it requires 10,000 kilowatt hours on a yearly scale, on the yearly level. So that's a really easy way, typically how it is done, but The problem is that if you oversize your heat pump, your energy demand will also be oversized. So if you have the same 7 kilowatts of static heat loss from before, we install a heat pump of 8 kilowatts, assuming the same 1000 full load hours, it's 8000 kilowatt hours instead of 7000. So it's important to factor away the oversizing or the potential oversizing of the heat pump, base this on the static heat loss instead of the size of the heat pump. Another way is to use a rule of thumb. So again, here there are rules of thumb in kilowatt hours per square meter, in kilowatt hours per cubic meter. Both are available. Another option is to work with heating degrees days. I will show an example on the next slide, but it's a little bit like working with the full load hours, but instead of taking into account the meteorological and the building itself in one number, the amount of full load hours, we can here make a distinction between the building insulation and the building physics and actually the meteorological influences like the temperature. So what is this heating degree days? We have a weather profile, we have meteorological measurements all over the globe, and we take the outside temperature and then we set a threshold temperature inside, above which or below which we should start heating. And then we look at every hour and we basically integrate or calculate the area when the temperature is below our set point temperature, and this is then summed up as being the heating degree days. Now this threshold temperature, it should be calculated or it takes into account things like inertia and emission systems and when your actual set point is. So it's not by definition the same temperature you enter on your thermostat. It's a little bit more complicated. For more information, you can visit the article. For the cooling demand, it's the same story. Again, here you typically work with full load hours. Again, you have also rule of thumbs for kilowatt hours or kilowatt hours per cubic meter. You also have cooling degree days, which is then the same as the heating degree days, but the other way around. So you again have a threshold, and when the temperature is above the threshold, you sum this area, and the total sum for an entire year is then the cooling degree days. The problem here is that it's a little bit more vague or complicated, let's say, than the heating degree days, because for heating, the heat losses are due to the difference between the internal and the out temperatures. But for cooling, most of the cooling demand is actually coming from solar gains. So it's not that trivial to just correlate the outside temperature with the cooling demand of the building. So therefore, if you really want to calculate the energy demand for cooling, there is also software for that, or you can use a certain building standard for that as well. Now the last energy demand is actually for domestic hot water. Now here there are also building standards, like for all the other things. For example, one's based on the number of occupants. We know that typically for a well-developed country, a person consumes around 1 megawatt hour per year of domestic hot water. There are also a rule of thumb for kilowatt hours per square meter. But one of the main questions related to domestic hot water I wanted to stress in this article is whether you should design for the occupants or for the building. Because let's say, for example, you have a building with 2 bedrooms and it's an elder people that's living there. So they have no children and they live there with two persons. Are you going to design your system with domestic hot water consumption for those 2 people? Or are you going to take into account that there is another 2-person bedroom so the building can actually house 4 occupants? Because that will give an effect, it will have an influence on how you should design your system. Now, given the fact that your geothermal bore field has a very long lifetime, up to 50 years, and it will see multiple owners, it's my opinion that it's better to design the system for the house than it is to design the system for the owners. Because if you want to make the argument that having a geothermal heat pump is actually an added value, it increases the value, the monetary value of your building, then it's important that it can also cope with other occupants. Now, of course, that's perhaps due to investment cost reasons and a difficult argument to make for some projects, but please take this into account that if you really want a robust system, you should design it based on the building and not the occupants' behavior or the occupants who live in the building at the moment. So this was basically everything I wanted to tell you in this article or in this video. For more information, you can read the article. There are some values, actual numerical values in there, which can be interesting for your project in early stages. But again, these are not written in stone, depending on your country, depending on your climate. More specifically, these rules can change, and you can have your own rule of thumb. If you think this video was interesting, please consider subscribing, sharing it with your colleagues, and I'm looking forward to seeing you in the next one. Take care. Bye.